So we were in numericals of Bell-Coleman cycle. Okay. So we were in example 2. So I'll just read it in short time. The atmospheric air at pressure 1 bar and temperature -5 degrees Celsius is drawn in the cylinder of the compressor of a Bell-Coleman refrigerating machine. It is compressed isentropically to a pressure of 5 bar. In the cooler, the compressed air is cooled to 15 degrees Celsius. So moment it says cooler, so cooler is at this position. Okay, so 2 to 3, they mean cooler. So cooler means air is being cooled, or the heat from air is transferred into the atmosphere. Okay, so air is cooled to 15 degrees Celsius, pressure remaining the same. Yes, why pressure remains same? Because this is a Bell-Coleman cycle. We have two isobaric processes. It is then expanded to a pressure of 1 bar in an expansion cylinder, from where it is passed to the cold chamber. Find first the work done per kg of air, second the COP of the plant. For air, assume law of expansion as PV raised to 1.2, and law for compression, it is PV raised to 1.4. And specific heat of air at constant pressure is equal to 1 kilojoule per kg Kelvin. So this is the case 3. So we had 3 cases in Bell-Coleman cycle. First was compression expansion. They both follow PV raised to gamma. Second was compression expansion. They both follow PV raised to n equal to constant. And third case we had compression follows separate and expansion follows separate law. So like for compression it may be PV raised to n. For expansion it may be PV raised to m. So we are in case 3. Compression here, compression follows PV raised to 1.4. And expansion follows PV raised to 1.2. Okay. So I just written the data. So here this is that 1 bar and I think somewhere here, yes, 5 bar it is there. So here I have drawn the PV diagram for Bell-Coleman cycle. So here I have 1 bar pressure. Okay. Here I have 5 bar pressure. So and what they have given also, where is the temperature? So -5 degree Celsius air is drawn in the cylinder of the compressor. So compression, where is the compression takes place? So this is the process for compression. This is the process for expansion. How to determine this? Because in compressor, pressure increases. So in this case, pressure is increasing from 1 to 2. Okay, so this is the compression process. So air is drawn at -5 degrees Celsius. So this will be the value of. So this will be the value for T1. When it says that it is compressed and cooled to 15 degrees Celsius. So it is cooled, not only compressed, it is cooled. So we are in point 3, it is cooled to 15 degrees Celsius. Okay. And other things, so other things I have written here in given. So T1 is given, T3 is given, and P1, P4 will be equal because these are isobaric processes, and P2 equal to P3 equal to 5 bar. Okay. So writing down the given is also one task. So you should understand the problem, draw the diagram. So when you draw the diagram and write the given the data, that time also most I would say that 40% of problem is in front of you. So like if you have experience or if you have practice, then within a minute you can solve the problem. Okay. So these are the steps we discussed in last lecture. So we have to calculate the COPs. The formula for COP is QL by W. So heat absorbed at low temperature, that is QL. W is power required in refrigeration. So this is the COP of refrigerator. Okay. So formula, like for in this case we have derived equal to Cp T1 minus T4 divided by compression work minus expander work. So we know for case 3, we have to calculate separately the compression work, we have to calculate separately the expander work. So these are the formula for compression work and expander work previously we have derived. So in this case, expansion index is 1.2, compression index is 1.4. Now in order to calculate this, here in this case what is unknown? So we know that T1 is given, T4 is given, okay, but T2 is unknown, T3 is given and T4 is unknown. Without this we cannot calculate above values. Okay, so I'll start calculating that. So we'll first calculate the temperature values. Okay, So we know that for isentropic processes, we can use the formulas. So like if I take a process of compression, so that will be T2 by T1 equal to, I can take P2 by P1 raised to gamma minus 1 upon gamma. So in this case, it is not gamma. So here, in this case, gamma is equal to 1.4. Okay. So T2 is unknown. T1, how much T1 is given? T1 is given 268 equal to how much P2 is given? I think P2 is 5 bar and P1 is 1 bar. That's to 1.4 minus 1 upon 1.4. Okay. So for compression, the index is 1.4. For expansion, the index is 1.2. Okay. So can anybody calculate this and tell me what will be the value for T2? So I hope you are with your notebook and pen and calculate with you. Even though you don't have calculate, then you can use the scientific calculator app in mobile. So you have to calculate this value of T2. So what is the answer? I think this should not take this much time. This is a one-step problem. So I have one answer. So I need a few more answers for confirmation. Devmare, though you have joined lately, no problem. Just calculate the value of T2. So it is on your screen, maybe. Okay, we have a new member, Chaitanya Kulkarni. Okay, so first time I have seen your name here. So Shirasat is saying same. Now what is meaning of same? So you mean to say same as above or okay. So Shirasat had saved his typing time by typing same. Okay. So I'll take that value 424. What I see on scale 424.46 Kelvin. Okay. So this is your T2. Similarly, you have to calculate for which is unknown here T4. So I can write for expansion process T3 by T4. Okay, T3 by T4 is equal to P3 by P4 raised to the index. So whatever the index I have to take here. So that index here in this case it is 1.2. So this will be 1.2 minus 1 divided by 1.2. So T3 how much is given? 288. 288 divided by T4 is equal to T3 is 5 bar, T1 is 1 bar, raised to 1.2 minus 1 of divided by 1.2. So calculate T4 same as you calculated in case of T2. Okay, so this time Anna Sir has given answer. Good, good. I thought he may say again, same again, but he has given answer. So thank you. So I'll take his answer, 220.24 Kelvin. Okay. Now your task is to calculate the QL. Okay, calculate the QL, then calculate the W. So for that you have to first calculate the compression work, then expander work, then you can calculate the COP. Okay. So the formulas are in front of you. You have to just put the values. Okay. So for compression, N is 1.4. Here for expander, M is 1.2. R for air. So R for air, we all know that is 287 kilojoule per Kelvin. Kg Kelvin. Sorry, kg Kelvin. So that you have to put here. T2 and T1 we have just T2 I have calculated and T4 is also calculated. So from that you can calculate the WC, WE, and you can put it in this equation. Cp is given. So Cp they have given as 1 kilojoule per kg Kelvin. Okay. And then you know the value of T1 and T4. So I think there will be no need for I explain in these things again. I expect the answer from you. So you first tell me the what will the value of WC, calculate WC. Okay, wait, I just put it blank here. Then calculate WE. Okay, calculate the QL and calculate the COP. So I hope you will calculate this by looking at the formulas. So anybody has calculated the compression work WC? I think some students will directly will give me the answer of COP because in Calc you can do this in one step, right? So in Calc you can put CP, T1, T4 value, and below you can in one step also you can do if you are a very pro player. So who are pro at Calc they can do this in one step, but it is not needed. You do it by step. Okay. So first you calculate the compression work, expander work, then you calculate the COP. Yes, any answers? I think this much time was sufficient to calculate for you. Okay, I will just start. So what will the compression work? So this will be like formula is given n upon n minus 1 into R into T1 minus T4. I hope that is clear. Sorry, that is T2 minus T1. So in this case, it is 1.4 divided by 1.4 minus 1. So this is 287. So remember, this is the kilojoule in kilojoules. Okay. So remember the unit. So whatever W will get, that will be also in kilojoules. So into T2, we have calculated as how much was it? Right? 424.46 minus T1 is how much? 268. Okay. So you'll get some value. Again, expander work. So this will be like m upon m minus 1, right? So R into T3 minus T4. So here it will be what they have given as 1.2 divided by 1.2 minus 1. So it is 287. Remember, this is also in kilojoules. So T3 is given 288, right? And this T4 we have calculated 220 point. How much it is? 24. So we have to calculate the expander work. Then we have to calculate the QL. QL is equal to Cp into T1 minus T4. So Cp is given 1 kilojoule per kg Kelvin into T1 is how much? 268 minus 220.24. So this will give some value. So this will be like kilojoule per kg. So all these values will be kilojoule per kg. This will be also kilojoule per kg. Then you can calculate QL. Then from this you can calculate the COP. So COP will be equal to QL divided by WC minus WE. And you will get the answer. So has anybody calculated? So I don't see any answers. So shall I calculate by myself? Okay, Nagras. So yes, sorry. 287 it is in joules. So the value for R equal to R for air. So we generated it is at 0.287 kilojoule per kg Kelvin. Sorry for this. So yes, this is in joules. So if I take 287, 287 will be joule per kg Kelvin. Sorry for this. Okay. So this will be like the joule. If you calculate this directly, this will be in joule. If you divide it by 1000, that will be kilojoule per kg. Okay. So I'll write here. I got the answer 159. 159 kilojoule per kg. The next expander expander I have calculated as 118.3. Okay. Then QL I have calculated as 48. So this will be like 48 divided by 159 minus 118.3. So COP in this case I have got it as 1.18. This will be your answer. Okay. Okay. So I think somebody has got the answer. Wakbode. Okay. You might have assumed some 287 as a kilojoule. Okay. So Rohit has calculated the right answer, that 1.179. So that will be approximately 1.18. Okay. So here it is 287 joule per kg Kelvin. So I hope others also got the same answer. So COP is 1.18. What else they have asked to calculate? So find the work done per kg of air, and second the COP of the plant. So work done per kg of air. So that will be that work done will be equal to minus WA. Okay, so this will be your answer. So what will be it is 159 minus 118.3. So that will be your answer. How much it is? 159 minus 118.3. So that comes out to be 40.7 kilojoule per kg. Okay, so we'll move to the next problem, and this will be our last problem. Okay, so this is also related to Bell-Coleman cycle. So this I will read it. Example number 3. So a dense air machine operates on a reverse Breton cycle, and it is required for capacity of 10 tons. The cooler pressure is 4.2 bar and refrigerator pressure is 1.4 bar. The air is cooled in the cooler at a temperature of 50 degrees Celsius, and the temperature of air at the inlet to the compressor is minus 20 degrees Celsius. Determine for the ideal cycle COP, second, mass of air circulated per minute, theoretical piston displacement of the compressor, theoretical piston displacement of the, again I think I have again written the same. Okay, so that is the third point. The fourth is net power per ton of refrigeration. Show the cycle on PV and TS planes. Okay, so first I will draw the PV and TS graphs. So wait, this is not correct. So let this be P and V, and okay, so this will be like 1, 2, 3, 4, and we know the cycle as 1 to 2, 2 to 3, 3 to 4, and 4 to 1. So in this case, they are not given the index. So I assume that this follows the PV raised to 1.4 equal to constant, and this also follows the PV raised to 1.4 equal to constant. So this is a Bell-Coleman cycle. 1 to 2 is isentropic compression, 2 to 3 is isobaric heat rejection, 3 to 4 is isentropic expansion, and 4 to 1 is isobaric heat extraction. Okay, so heat is being extracted, so that is a QL. Heat is being released to the atmosphere, that is a QH. So this is the PV diagram. If I draw the TS diagram, so TS, so it is much easier to draw on board in classroom, but this tab it is a little bit difficult. Right. So 1 to 2 is compression, 2 to 3 is heat rejection, 3 to 4 is again isentropic expansion, 4 to 1 is isobaric heat extraction. So heat is released, heat is extracted. So this is QL, this is QH. So that I have done. I have showed it on the PV and TS planes. Now I will read the problem. So they are given the problem. In that problem, they are given the refrigeration capacity of 10 TR, right? So capacity is given. So I'll write down the whatever given in the for problem. So capacity is 10 TR. Then cooler pressure is 4.2 bar. So cooler pressure, what they mean by that? That is P3 equal to P4. That is here 4.2 bar. Then they are given the refrigerator pressure is 1.4 bar. So this will be the refrigerator pressure, that is 1.4 bar. The air is cooled in the cooler at temperature of 50 degrees Celsius. So this is the cooler. Okay, so this is your cooler point. So here the temperature it is 50 degrees Celsius. The temperature of air at the inlet to compressor is minus 20 degrees Celsius. So here it is compressor. So the temperature they are given as minus 20 degrees Celsius. So first we have to calculate the COP. So here the gamma we can assume it as 1.4. So directly we have the formula that COP is equal to 1 divided by RP raised to gamma minus 1 upon gamma whole minus 1. So that formula we have, we can use that formula. Second is mass of air circulated per minute. So here they have given the capacity. Then we have to calculate the QL. From QL and the capacity we can calculate the mass of air circulated. Then the other things we'll see later, that piston displacement and net power per ton of refrigeration. So net power. So in this case, I will first write down the given data. So here P1 is equal to P4 is equal to 1.5 bar. Sorry, 1.4 bar. Then P2 is equal to P3 is equal to yes 4.2 bar. Then they have given T1 as minus 20 degrees Celsius. So I will convert this into Kelvin. So this will be this plus 273. So that will be 253 Kelvin. Then what is given in this case? T3 is given as T3 is given as 50 degrees Celsius. So 50 plus 273. So that will be 83, 93, 303, 313 and 323. So that will be 323 Kelvin. Okay. So this is the given data, and from this we have to calculate the, first we'll calculate the COP. So first is calculation of COP. So in this case you can directly calculate the COP as 1 divided by RP raised to 1 minus gamma minus 1 upon gamma minus 1. So here RP can take any ratio you can take, either you can take P3 by P4 or you can take P2 by P1. So both will be same. So that will be 4.2 divided by 1.4. So I think this is the 3, right? So this is the like अपन तो 14 का पढ़ा, ठीक है? ठीक है? And gamma is given as 1. So that is air. If they don't give the value of gamma, so by default for air the gamma value is 1.4. So COP is equal to 1 divided by 3 raised to 1.4 minus 1 divided by 1.4. This expression minus 1. So calculate this and tell me the answer. We calculate the answer. Meanwhile, those who didn't understand this pressure ratio, I will tell with the help of the diagram. So see pressure ratio, what we are doing, if I take compression ratio, so compression ratio means while compressing the air from 1 to 2, I have to take the ratio of P2 by P1. So P2 is delivery pressure, P1 is suction pressure. Now, in the case of Bell-Coleman cycle, we have an advantage that we have two isobaric processes. So, pressure at P2 is equal to pressure at P3. Pressure at P3, that is the cooler pressure, and divided by P1 is equal to P4. This is possible only in case of only Bell-Coleman cycles. So, air is expanded from P3 pressure to P4 pressure. So, that is the idea about pressure ratio. Okay. So yes, anybody has calculated the COP? So why only one person or two persons are calculating? So shall I call by your name? Yes, Pranati Bosle. Pranati Bosle, please calculate it and tell me the answer. Hello, Pranati, are you following? So I hope you are calculating. So calculate and tell me the answer. So I guess she is not replying. I'll move to the next person. So who is answer? Sunil Sonar, I think you have replied or you didn't calculate. So Sunil Sonar, please calculate. So this is a one-step calculation. This you can do easily, on your CALC if you have. So I guess if you are having your CALC, right? If you don't have, no problem. On Google Store there is an app like a scientific calculator that you can calculate. It is the same as your CALC. So in that also you can do the calculation. Okay. So I also do the same. I have that app in my mobile. I do the calculation on the same CALC. I don't have that physical CALC now. I think I have lost somewhere. Okay. So Pranati has replied, good, good. So she is saying that COP is 2.712. So I think others also has replied the same. So I'll take Pranati's answer. So that will be 2.712. So this will be your first answer. So that is nothing but your theoretical COP. Okay. Now next thing is calculation of your rate of circulation of air. So we have to calculate the mass of it. Okay. So in this case, refrigeration capacity is equal to what they have given. In this case, it is 10 TR. Okay. So 10 TR, can you convert it into kilowatt? So how to convert tons into kilowatt? So we have to multiply by 3.5. So multiply this 3.5. So I think that is straightforward. So we'll get 35 kilowatt. Next, we have to calculate the heat extracted. So what this gives you actually? So this gives you kilowatt means what? Kilojoule per second. Okay. Next, I will calculate the cooling capacity or heat extracted. So that is nothing but QL. So formula for QL we all know, that is C into Cp into T1 minus T4. So here it is air and they have not given the value of Cp. So we can take directly it as a 1 kilojoule per kg Kelvin. So that will be 1 kilojoule per kg Kelvin and T1 minus T4. So T1 they have given in this case. T1 is given 253 minus T4 is not given. So T4 we have to calculate. So we have to do two calculations for I think for T4 only. I don't think we have to do calculation for T2. Okay. So similarly we have to calculate here also like we calculated in last problem. So here I will write it as, so let us calculate this T2, right? T2 by T1 raised to gamma, sorry, not raised to. So for isentropic processes, we know we can use this relation. So equal to P2 by P1 raised to gamma minus 1 upon gamma. So here in this case, pressure is given as 4.2 divided by 1.4. So raised to 1.4 minus 1 divided by 1.4. Okay. So from this you can calculate the T2. So T1 is given as 253. Okay. So from this you can calculate the T2 and how to calculate T4. So we have the relation for expansion, that is T3 by T4 is equal to P3 by P4 raised to gamma minus 1 upon gamma, and this again will be same as above, so that will be 1.4 raised to 1.4 minus 1 divided by 1.4. So in this case T3 is given, so T3 is given as 323. Okay. From this you can calculate T4. Okay, so I have calculated T2 as 5, not the 5. Can you calculate? So here it will be not the 5, so this will be 346 Kelvin. Okay, and T4 will be 236 Kelvin. Okay, so I have two values. Then I have to put this value of T4 here. So this value I have to put here and calculate the QL. So can you calculate QL? So QL will be equal to 253 minus 233, so that into 1. So that will be a straight calculation. 246 plus 7. I think that will be 17. So that will be 17 kilojoule per kg, right? So yes, Nistane, she is very fast. She has given the answer before I asked. Yes, good, Nistane. So QL is 17 kilojoule per kg. Then how to calculate the mass? So mass will be mass flow rate of air equal to, so see the units here. Okay, so here unit is kilojoule per second, here it is unit is kilojoule per kg. if I divide kilojoule per second divided by kilojoule per kg, ultimately what I will get, kilojoule will cancel. This kg will go in numerator, second will be in denominator. So ultimately I will get kilojoule per second. So mass flow rate, I can take this as capacity, okay, divided by QL, heat extracted. So here it will be 35 divided by 17. So this will be approximately 2 point something. So that is 2.1. So I'm very glad that you all are calculating even before I ask. So Pradyumna has one answer. Tadmare, yes, Swapnil Tadmare has a very constant performance. And Nestane, good, 2.05. We can take it as a 2.1. So this is our next answer, 2.1. What will the unit? So unit will be kg per second. Right? So I'll just write here again on the maybe on next slide. Okay, so mass flow rate we have calculated it as 2.1 kilojoule per second. So this is your answer 2. Next we have to calculate the theoretical piston displacement of compressor. Now I don't know if you remember, so you have studied a chapter in your applied thermodynamics. So last chapter was reciprocating air compressors. Okay, so that diagram is kind of similar to Bell-Coleman cycle. Okay, so this will be like PV diagram. 1, 2, 3, 4. So this was the diagram when we studied reciprocating air compressor. So this represents the cycle inside reciprocating air compressor. So air is being taken. So this is a piston at BDC. Then it compresses the air to the BDC. Then air is delivered at 3. Okay. So air is not delivered at 2. Air is delivered at 3. And again we have this start from 4. It takes the air inside, then it is compressed and the cycle repeats. So in this case, what they mean by theoretical displacement of piston, so that means obviously this point. Okay, so we have to calculate the V1, so that will be the displacement of piston. And next they have asked for theoretical displacement of expander, so that is means this. So this is the end of expansion, so we have to calculate the V4. So our aim is here to calculate V1 and V4. So these are the displacement values. Okay. Now, if you see V1, so for like if I want to calculate third point, so third point is theoretical displacement of compressor. So that will be V1. Now I can use the relation ideal gas equation, that is PV is equal to MRT, right? So I'll continue that here. So in this case, I can use the equation. So that will be like P1 V1 equal to mass flow rate of air into R into T1. So V1 I can directly calculate it from like mass flow rate of air into R into T1 divided by P1. Okay. So mass flow rate of air we have calculated as 2.1 into R we can take 287. Okay. T1, how much they have given T1? So T1 is 253 Kelvin. So this will be 253 Kelvin divided by P1. So P1 is given 1.4 bar. So that bar we have to convert it into Pascal. So that will be 1.4 into 10 to power 5. So calculate this value. So Pradyumna, please calculate correctly. I'm glad that you are applying. You had a very good breakfast today, so you are full of energy. But while calculating, please take care. And because I have got another answer from Nistan as 1.08, so there is a difference between your two answers. Okay. Okay, so I have another answer from Abhishek Sivsagar. Again, Swapnil Tadmar has given answer 1.08. So Swapnil, we never met personally, but I'm very like excited to meet you because your performance is very consistent. Pooja Kamble has now joined, so we welcome her to the class. So Pooja, that timing was 10 a.m. So you are joined at 11 a.m. Okay. So Pooja, so we are solving the problems of Bell-Coleman cycle. So like we are in mid of one problem. Okay. So you can continue this problem by solving the given equation on your calci. Okay. So Pooja, calculate the value of V1. So I'll go with the other answers. 1.08, right? So 1.08. What will be the unit? So you are given the answer, but none of you has given the unit. So what will the unit in this case? So whether it will be meter cube or it will be meter cube per second, what will the answer? What will the unit? Can anybody answer? Okay, yes. So meter cube per second. Why? Because here, if you see the unit of mass flow rate, so we have calculated it as kilojoule, sorry, kilogram per second. So that per second will be here in the denominator, and as usual, volume will be in meter cube. So that would be meter cube per second. Okay. So good. So next thing we have to calculate the V4. So I hope all have got the same answer for V1, right? So how to calculate V4? So if you see here, this process, it is isobaric process. So that is a constant pressure process. So we have in physics, we have what we call it as the Charles law, right? Right. So Charles law said that at constant pressure, that volume and that temperature, okay, so they are directly proportional. So like by Charles law, what it says, at constant pressure, that V is directly proportional to T. So here we can take that. So here we can take the ratios directly. So we can take V4 divided by T4 is equal to V1 divided by T1. Now in this case, V4 is unknown, but we know the T4. T4 we have calculated it as 236. 236 is equal to V1. So, okay, V1 we have just calculated 1.08 divided by T1. T1 also, uh, T4 is 236 and T1 is 253. So from this we can calculate the V4. Okay, so calculate V4. So I got some answers. So I'll write it down. So one is saying 1.01, 1.007. Okay. So I'll write the answer as a 1 point. So let's say 1 only, right? So I'll take 1 meter cube per second. So we have got the answer here and here. So V1 is theoretical piston displacement in compressor, and V4 is theoretical piston displacement in expander. Now next we have to calculate the net power per turn of refrigerator. So next term, so net power means we have to calculate the W. Okay. So how to calculate W? So we have calculated the COP. Now COP is equal to QL divided by W. So QL is also, I think, somewhere we have calculated. So yes, here we have calculated the QL. So we have the QL, we have the COP, and we have to calculate the W. Okay. So I'll again insert one more slide, and then we can solve it. So COP is equal to QL divided by W. COP we have calculated as 2.7. How much it was? So 2.712. 2.712 is equal to, this was 17 divided by W. So you have to calculate the W. So it will be, I think, 17 divided by 2.5. So that will be around what? 6 or something. I don't know how much. This should be something 6 something. It should be there. So yes, I got the answer. So as a 6.26. So W is equal to 6.26. Now what will be the units here again? Okay, so unit will be kilojoule per kg. Why? Because the unit of QL is, we have taken it as kilojoule per kg. So always take care of units. Okay, so 6.26. So in competitive exams, units is not that much big issue. If you are going for MCQ type question, they only will ask you the value. Okay, but if you are going some exams like in IES, that is Indian Engineering Services, in that in main exam you have to write the papers. So that is a written exam. So in written papers you have to solve problems on paper. In that that units will be counted. Okay, even in your university. But in university, as an examiner, I know if you get the right answer, you don't bother about your units. But that is very good practice if you always look for the units. Okay. So there may be a confusion between kilojoule and joule. If you write the units, there won't be any confusion. Okay. So that is it. That is the end of this problem. Though it looks like in 4 slides, this is a problem of 1.5 page. Right. So at the end of this, I will give you some numericals. So I will give you one document or a PDF for your practice. I will put it on our group. So I will give the notes of this up to this point. Okay. Also, we have prepared one study material sheet. In that we have given the links for our drive files. So I have uploaded all these notes and MCQs on my drive. And we all, like not only RAC, others like AC, or they have also given their links in that Excel sheet. So soon I will share that Excel sheet with you. Okay, right. So I'll take again a quick revision. So up to now, what we have done, we have started with the reverse Carnot cycle, then we have seen its limitations. Then we went for Bell-Coleman cycle, which is a modification of the reverse Carnot cycle. Bell-Coleman cycle has two isobaric processes and two isentropic processes. Then we did the derivation, right, for the COP. So we had three cases. So one was expansion and compression. They both follow PV raised to gamma. Second was they both follow PV raised to n, and n is not equal to gamma. And third was expansion and compression. They both have separate indices. So compression has suppose 1.4, expansion has 1.2. So this was the derivation. Then we solved some problems. So that was like theoretical treatment for the Bell-Coleman cycle. Now we'll see what are the air standards, air cooling systems. Okay, so the refrigeration systems or cooling system, they are using air. So commercially we use the refrigerants, but there are some systems, like if you take the example of aircraft. So in case of aircrafts, they are using air for cooling purposes. Okay. So we'll move to further. Right. So we'll see what are the advantages of air refrigeration system. So it is first, it is cheap and abundant refrigerant, highly reliable. Air is used as refrigerant, which is easily available and inexpensive. Charging a refrigerant is very easy. Now charging. Okay, so what is meant by charging? So when you design a system, okay, so inside the system, that the refrigerant must flow through the pipes. Now initially what they do, they fill all these pipes with the refrigerant. So ज्यावेळेस आपण एक सिस्टीम तयार करतो, त्यातल्या ज्या सगळ्या ट्यूब्स आहेत, कंडेन्सर ट्यूब्स असतील, इव्हॅपोरेटर ट्यूब्स असतील, त्या इनिशियली रेफ्रिजरंटनी भरल्या जातात. त्यानंतर आपण काय करतो, त्यातला फ्लो चालू करतो. सो दॅट इज नथिंग बट चार्जिंग. So it is similar to your phone charging, like you charge your phone and then you use it. So similarly, pipes are charged with refrigerants. So charging of refrigerant is very easy. Design and construction is simple, no complicated parts, and its maintenance cost is low. Fourth is refrigerant, that is air, is non-toxic, non-flammable, non-corrosive. There is no danger of any kind of leakage. So even if that system has a leakage, so what will come out of leakage? That will be nothing but air. So air will be leaked, and that is non-toxic and non-flammable. Okay. So there are some systems like ammonia systems are there. So they are very good at their performance. Their COP is very good. But the thing with ammonia is it is toxic. Like if there is any leakage in the system, it is very toxic to human beings. But air is not non-toxic. The fifth is there is no phase change. So for in case of air, right? So there is no phase change. So in case of water, we have phase change like ice, water, and then steam. But in case of air, there is no phase change. The cold air can be directly used for refrigeration. It is useful in aircraft refrigeration at high altitudes. So what is that? We'll see in couple of minutes. There will be no significant change in the performance of air refrigeration if it is operated much away from its design conditions. Yes. So whenever you design a system, so you have specified some design and operating conditions. So even if the system deviates from that conditions, there will be no significant change in its performance. Okay, so these are some advantages of using air refrigeration systems. Similarly, so like there are two sides of coins. So we have seen only one side, that is advantages. So there is another side of the coin, that is disadvantages. What are the disadvantages? So we have lower COP compared to other refrigeration cycles. So we have solved the problems. So if you take a look at the problems, you will see that COP is in the range of 1 to 2. Okay, so maximally it will go up to 2.5, but it won't go much beyond of 5. Okay, so if you take example of your air conditioning in the room, so we have split air conditioner. So their COP or their EER, energy efficiency ratio, that is very good. But in case of air refrigeration system, we have very low COP. Second, running cost is high. Okay. Third is the mass of air required to circulate in the system is very high when compared to other type of refrigeration cycle due to low specific heat capacity. So we know that water is having more heat capacity than air. That is why in case of IC engines, we have seen we have air cooled jackets. So for air cooling, we have fins, and in case of water, we have water cooled jackets. So what is the advantage of using water in that case? Because water has greater specific heat. It carries more heat per kg of water. So like that mass. So if a substance or if a fluid is having more specific heat, then we will require very less amount of it. If a fluid is having very less specific heat, as in case of air. So air is having very less specific heat, so we require very large mass of air. Okay. So fourth is system components are bulky, large space per ton of refrigeration. The chance of frosting at expander is more due to moisture content in the air. Frosting means first we have what we call it as dews. तर आपण बघतो की दव तयार होत असतं सकाळी, मोस्टली हिवाळ्यात किंवा पावसाळ्यात आपण बघतो. मोस्टली हिवाळ्यात होत असतं की पाण्याचे दव तयार होतात, त्यातून पुढे काय होतं, फ्रॉस्टिंग होतं. तर आपल्या इथं फ्रॉस्टिंग होत नाही मोस्टली इन केस ऑफ माउंटन रिजन्स लाईक कुलू मनाली, or if you take example of European countries, they have this they face this situation called frosting. तिथं बर्फ पडतो in certain months of year. Okay, so best month to go to Manali is it is said that January. So I went in the month of May. So that time we came to know that if you come in the month of January, then you could see the rainfall, right? Okay. So last is air contains pollutant particles. So do regular cleaning of air filter in open system. So that is very common that air has suspended particles. Because of that, we need filters, right? So Rohit is saying thank you, sir. So I think Rohit is planning to go to Kulu Manali. So maybe he's saying thank you that I have warned him to go in the month of January. Huh? Is it right? Okay. Okay. Right. Okay. So we have seen the advantages and disadvantages. Then there are two types of system. First we have open cycle and second we have a closed cycle. So in case of open cycle, as we see, so we have four components. So we have solved problems on this. So we know there is compressor, there is expander, and then we have a cooling coil, and the main part of this system is refrigerator. So we are using air to cool a space. So this is our main objective. Okay. So in case of open cycle, what happens? Air comes in the space, it cools the space, and that air is thrown out. So what happens? Every time compressor takes fresh air. Okay, so though this figure is not applying that concept, but in case of open system, what happens? Each time compressor takes in the fresh air, and that air is been compressed. Okay, its temperature is reduced, then it is expanded, and then what happens? That air is used for the refrigeration purpose. Similarly, we have On other side we have closed cycle. In this what happens? So we are using air. So if I take air inside, so it compresses the air, then we cool the air, reduces its temperature, then that air is passed to the expander. What happens in expander? This pressure reduces, then that air is passed to the refrigeration space. Now in this case what happens? That air is again used, but in this case we are using air to cool a brine water. Now brine water, in simple terms we can call it as salt water. So that is generally used in chilled water system. So what we are doing in this case, we are using air. With the help of air we are cooling the water, and then this water is used for refrigeration. Okay, like in this case we are directly using air for refrigeration. Okay, so I'll give some time. You draw these two diagrams in a very simple way that you can draw. So in both these cases, the cycle remains same. That is the Bell-Coleman cycle, which we have seen earlier, and we have solved the problems also. So like this, we have a Bell-Coleman cycle. So 1 to 2 is compression, 2 to 3 is cooling, 3 to 4 is expansion in expander, and 4 to 1 is heat extraction. So here we can see that 1 to 2 is compression. We are using a compressor here. Then 2 to 3 is cooling. So we are using a condenser type system. So we have condenser. We cool this air with the help of cooling water. Then this air is being expanded in expander. So 3 to 4 in this diagram. In this Bell-Coleman cycle, we have seen 3 to 4 is a expansion process. So 3 to 4 is a expander, and 4, that cooled air we are passing it to the refrigerator. So 4 to 1 is a cooling process. So this is our main objective. So I'll give you 5 more minutes and draw it. So don't draw it like as it is. So you can draw in your simple way, like compressor and expander. Okay, so this will be our last bit of this lecture. Uh, Next lecture we'll go for various types of air refrigeration systems, especially in aircrafts. So in aircrafts, they are using this air refrigeration system. The air outside is being taken in, and that air is processed. It is cooled, and whatever required air at required temperature and pressure, it is passed to the passenger. Okay. What happens in the case of aircrafts as you go in higher altitudes? So like aircrafts are generally at the altitude of 10,000 meters and 20,000 meters. So in between them, aircrafts fly. So as you go up in the sky, the pressure decreases. So here we are habitual for a pressure of 1 bar and suppose 300 Kelvin degree temperature. But as you go up in the sky, so the pressure reduces to like what, zero point 0.2 bar, and at zero point 0.2 bar the temperature is also very low. So temperature is in minus 20, minus 30 degrees Celsius. That is a good thing for refrigeration, but we cannot take that air directly inside. Okay, so what happens if you take air at zero point 0.2 bar inside a aircraft which is to be maintained at 1 bar? म्हणजे काय करतोय आपण, 0.2 बारची एअर 1 पॉईंट बारला करतो, म्हणजे आपण काय करतोय, कॉम्प्रेशन करतोय. कॉम्प्रेशन मध्ये आपण काय करतो, प्रेशर वाढवत असतो. त्यामध्ये काय होतं, टेम्परेचर देखील वाढतं. म्हणजे तुम्ही डायरेक्टली जरी एअर आत घेऊ शकत असता तरी त्याचं काय होणार आहे, टेम्परेचर वाढणार आहे. मग हा प्रॉब्लेम आहे. प्लस त्या इंजिन मधले काही हीट जनरेशन होत असते. फ्लाय होताना सरफेस फ्रिक्शनमुळे देखील सरफेसला हीट जनरेट होत असते. तर असे बरेचसे फॅक्टर असतात त्याच्यामुळं एअरक्राफ्ट मधले किंवा एअरप्लेन मधली हीट तयार होत असते. तर ती हीट घालवायची असेल तर आपल्याला काय लागणार आहे, रेफ्रिजरेशन सिस्टीम लागणार आहे. सो विल सी दोज सिस्टीम इन नेक्स्ट लेक्चर. ओके. तर बाहेर थंड एअर आहे म्हणून आपण एअरक्राफ्ट मध्ये खिडकी उघडू शकत नाही, ठीक आहे. जसं आपण बसमध्ये करतो, खिडकी उघडतो, थंड हवा येतं, आपल्याला वाटतं हा. पण इन केस ऑफ एअरक्राफ्ट वी कॅनॉट डू दॅट. यू मे हॅव सीन सम मूवीज ज्यामध्ये ते एक्झिट डोअर उघडतात आणि लोक आतून बाहेर उडून जातात. सो दॅट इज ड्यू टू प्रेशर डिफरन्स. बाहेरचं प्रेशर फार कमी असतं, आतलं प्रेशर जास्त असतं. बिकॉज ऑफ प्रेशर डिफरन्स, इफ यू ओपन विंडो, इफ यू ओपन द डोअर इन द फ्लाइट, disaster may happen. So that is the case. For that, we require a dedicated refrigeration system to maintain an indoor environment. So we'll see that in next lecture. Okay. So have you drawn this diagram? So I hope you have noted down the points, also this diagram. Please reply, anybody? Okay, so as you have completed the notes, I will stop today. Next lecture we'll go for aircraft refrigeration system. So what are the refrigeration system or air conditioning system we are using in case of aircrafts or aeroplanes? Okay, so quickly I will take the attendance with the help of meet attendance. Then we can stop. So total 26 people are here. Yes. So with the help of this meet attendance extension, I have taken your attendance. So thank you for being here. You can leave the meeting.
Sir, I have one doubt.
Who's this?
नितीन जाधव.
Okay, Vaibhav. बोल की.
काय ठीक आहे, काय चाललंय?
Hello. Hello. I think we have lost him.
ए सोन्या
तुम्हाला